Hello and welcome. In the last video we looked at the linearization of a function, which helped us approximate the values of a function. But if we want to approximate the change in values of a function, then we're going to use what are called differentials. Differentials. To start, remember that we had this Leibniz notation, dy dx equals f prime of x. Like dy dx is just another way of writing the derivative of y with respect to x. And a way of writing that using function notation would be f prime of x, right? But you can think of f prime of x as the slope of the tangent line, right? The slope of the tangent line. Which is a rise over run. Any slope you can think of as a rise over run, a change in the y values over change in x values. So what we're going to do in this section, or this packet, is we're going to treat dy as a rise along the tangent line and dx as a run along a tangent line. So these dy and dx are actually going to be representing some values here. So the differential dx we're going to consider to be an independent variable, one that we have control over and we can change, and that those values of dx are going to influence the values of dy. If these are two different variables, if we're treating dy and dx as two different variables, what we could do is we could multiply the dx over to the right to be with the f prime of x, and we would get something like dy is equal to f prime of x dx. So here, when we have it set up like this, if we change the values of dx, then those will affect changes in the values of dy, right? So this is like a variable dx that we can change, which will influence what the values of dy are. In other words, if we change the run along a tangent line, that's going to change the rise that we travel along that tangent line as well. The longer the run, the longer the rise, generally speaking. So here in the picture we have just a general function, and we have a tangent line at x equals a. So if we move over, so if we move a run of dx, so move over to the right by dx, then the distance that we have to travel in the y direction is what dy is. So that way the slope of this tangent line is dy over dx. It's the rise over run. So that's the picture that we're looking at here. We're traveling along the tangent line to figure out the approximated rate at which the function is changing, or the change in the function values. All right, so example 2 says find dy if y equals x to the 5th plus 37x. So to find dy, we can find first the derivative of the function and then just multiply it by dx, and that'll be what dy is defined to be. So let's do that over here, but actually before we do that, let's use function notation, just because our definition of dy involved a function. F prime of x would be the derivative of that function, so we'll just define the function to be f of x equals x to the 5th plus 37x. So now we're going to write dy is f prime of x dx, where f prime of x is just the derivative of our function, which is going to be 5x to the 4th plus 37. And that's it. That's dy. So this basically gives us an equation so that if we change dx and plug in an x value here, that's going to give us a corresponding dy. If we give a run, we'll get from this equation the corresponding rise to stay on the tangent line. Now it says find dy when x is equal to 1 and dx is equal to 0.2. Well, that's no problem. We can just plug in x equals 1 and dx equals 0.2. So there's the 1 going right there. There's the 0.2 going right there. and if you evaluate this, you get 8.4. So in other words, if the run is 0.2, and you're at this x value, your point of tangency is x equals 1, then your rise along the tangent line will be 8.4. Your change in your y values will be 8.4. Now the second part of example 2 says, find the true change of the function which is represented by delta y. So delta y is representing the actual change in the function values. dy just represents, like, if you move to the right by dx, how far you'd have to move up to get to the tangent line. So that's the change in the tangent line, you might say. Whereas delta y says if you move over to the right by dx, delta y represents the change in the y values up to the actual function itself. So this delta y is the actual change in the function values. It's the original function value and then to the next function value, whatever that is. So you can say it's like the final function value minus the initial function value. Final y minus initial y. Well, to get that, we would take the final y minus the initial y. So here, the starting x value is 1. The ending x value is 1 plus 0.2. If we wanted to put these x values into our picture here, this would be like 1, and this would be 1 plus 0.2, which is 1.2. Let me write that a little bit better. So we're going to get f of 1.2 minus f of 1 to get the change in the y values. So we could even label them over here. This is like f of 1 and f of 1.2. The change in the y values are the difference between these two. So we have f of 1.2 minus f of 1. Now the function is x to the 5th plus 37x. That's where we're plugging these 1.2 and the 1 into. So we have 1.2 to the 5th plus 37 times 1.2 minus 1 to the 5th plus 37 times 1. Gotta sit up straight like my mom always told me to. 8.88832 is what you end up getting. Okay, so that's the true change in the function values, which is not too far off from the approximate change of the function values that the tangent line was giving us. If you walk along the tangent line, you get a change in y of 8.4. If you walk along the function itself, you get a tangent line or change in the y values of 8.88832. So there's a difference of about 0.4, well, 0.488832 to be exact, which is not too far off considering the range of y values that we're thinking about. In fact, let's calculate that. So it says now calculate the approximation error, which is the absolute value of delta y minus dy. So that's the difference between the true change in the function values and the approximated change in the function values given by the tangent line. Well, to get that, we will take delta y minus dy. So it's 0.88832 minus 8.4, and we get 0.48832. Kind of said out loud what the next part was going to be. Oops. That was a spoiler, I guess. All right, so the absolute values I just want to mention is there because then all of the error are going to be positive error. You could talk about negative error, but usually a lot of times error is written as positive in terms of positive values. Okay, so those are differentials. Thanks for watching, and see you in the next video.